Hey there, brand new academic year, brand new haircut, and what I'm going to hopefully show you is a fantastic brand new video on the first demonstration I've actually shown to my year 9 GCSE classes. This is actually something that will be very commonly shown across many GCSE classes right at the very beginning of the course, because what we have to do is we have to start with the basics, start with the foundation. So one of the early topics that's very commonly taught is to do with solids, liquids and gases, and it's actually particle theory and diffusion. So what I'm going to do is I'm going to show you a diffusion tube. I'm going to show you the two chemicals that we actually use to demonstrate diffusion taking place. I'm going to show you the results and I'll show you an explanation as to how to interpret those results, which is not very easy, particularly for GCSE students, because of the concept of lighter molecules moving faster. That can be quite a puzzling one, but I'll take you through it and hopefully we'll get some fantastic results happening very shortly. Okay, stay tuned. So here we have it. We have our diffusion tube, which is just basically a glass cylinder. It's pretty long, so I've got you on a wide shot here. At one end, I'm going to be putting one volatile liquid. Volatile means that it can turn from a liquid to a gaseous form very easily, relatively easy at room temperature. I'm going to be putting concentrated hydrochloric acid on that end over there. And on this end over here, swish, I'm going to be using another volatile liquid. That's going to be concentrated ammonia. So these are two different molecules and they have different masses. They have different weights because they're made up of different atoms. And what I'm going to do is I'm going to use these bungs to seal the ends as soon as I introduce the liquids into the ends of the diffusion tube. So that stops air currents from interfering from the outside. It's quite useful because when we're doing this experiment, we're using some pretty strong chemicals here. So we want to try and keep it as safe as possible. I've got some black paper over here to help show the results. When these two gases meet, we should be able to see a white cloud forming, and that white cloud is a substance called ammonium chloride. So depending on which gas moves faster, we could have it down that end or we could have it this end. Okay, I'm going to soak the liquids in cotton wool, and then I'm going to, as quickly as I can, place the cotton wool soaked liquids at either end and seal them, and then we'll just see what the results are and we'll talk about the results. I'm going to be using these cotton balls. So what I'm going to do is I'm going to keep that in there, just pour out a little bit of the acid, just enough to soak it up. This is smelling very sharp, so I'm not going to breathe it in at all. Just need that much. Just going to keep it in there, and then I'm going to pop a little watch glass on there just to minimise the amount of gases that come from there. This is concentrated hydrochloric acid, and the gas that can come from there is hydrogen chloride gas. Do exactly the same thing at the other end to get the ammonia ready. Just pour the ammonia very carefully just down the side and just soak up the ammonia in the cotton wool ball as much as possible. Just going to roll it around just to soak up as much as I can, and then just before the next stage I'm going to use the watch glass just to cover it so that I minimise any fumes that are coming from there. I'm using a ventilated laboratory. So the next stage that I'm going to do is I'm going to take that ball, pop it in here, put the bung on, and do exactly the same thing on the other side. I have to do this as quickly as I can. Okay, I've got to do this very quickly, and once I've started, there's no going back. So here we go. I'm going to start off with this end. So Ball now placed inside the diffusion tube. Bung squeezed on there. Other end, ball into the diffusion tube, bung squeezed onto here. And now we wait. So we've got some results now, and what I'm going to do is I'm just going to show you. I've got this black paper to highlight, but I think it's pretty clear as to where things are coming together for a reaction. So this is the left-hand side, absolutely transparent here. There's probably just a bit of glaze on the cover. That's just from rinsing from previous tries. And going all the way over here, we suddenly see this. Okay, it's a very misty, white, smoky cloud. Okay. And then if we go beyond there, it's transparent again. So it's very clear that the cloud has formed on this end, on this side, further towards this end than on that end. And then the question then becomes, well, how could that be? These particles over here, these hydrogen chloride particles, actually have a relative molecular mass of 36.5, whereas these particles over here that come from the ammonia end actually have a relative molecular mass of 17. The mass of these particles is pretty much double the mass of these particles over here. People do get confused about this within chemistry because we don't explore in greater detail the concept of the principle of conservation of momentum, which is pretty much what's driving this. But a nice way to think about it in terms of being able to understand it is this. Imagine that you have a very low mass gas particle and it's traveling from this cotton wool ball over here. If it collides with an air particle traveling at a set speed, the smaller mass particle will bounce further and with a higher speed away from where that collision took place, in comparison to a larger particle in terms of larger mass. And if that larger mass particle underwent exactly the same collision, it would not necessarily move further and with a faster speed. And that can be quite difficult again for us to imagine, but that's the explanation that's given in the books. One explanation that I like to give, which my students find quite amusing, is this. So say, for example, there's an accidental collision as you're walking down the corridor. So imagine that you're going, during the course of your schooling day, walking down the corridor, and accidentally you have two collisions. You're not going to change speed for this particular analogy. But let's say the first collision is with a year 12 student. These year 12 students tend to be a little more bigger and a little bit more grown up. So if you walked into them and there was an accidental collision, maybe you brushed past them, perhaps they may not necessarily move too far away from where they were traveling. They may deviate a little. However, if you walked at the same pace into the second collision and you bumped into a very small and very slight year 7 student, that student could actually bounce quite far away from where the collision took place because they're smaller and they're lighter. Now you can imagine that the small mass year 7 student is analogous to the smaller molecule of ammonia, NH3. And the larger year 12 person could actually be analogous to the larger mass particle, which is hydrogen chloride. So the smaller the actual molecule, the quicker it seems to be zipping around inside that diffusion tube. So it travels a further distance in the time that's being given to it. The time limit ends when both of those chemicals react with each other. And where both of those chemicals react with each other, we actually see with this particular chemical reaction that there is a white cloud, a white smoky cloud. So in the time it took for both of the gases to meet each other, the lighter particles actually moved a further distance. This is fantastic for us to actually study because it actually gives us concrete evidence that not all gas particles are the same. It actually suggests to us that the mass, specifically the molecular mass of the substances that we're studying, could make a difference to the rate of diffusion. Rate being the change of distance that the particle travels on average over time. What we also need to bear in mind as a final thought is that the particles that are traveling within the diffusion tube as they leave the cotton wool ball are actually traveling in random directions. But this kind of averages out. So you could get one collision that sends a volatile chemical molecule in the opposite direction. That's fine because there could be an air particle that bounces it back into the direction of the other cotton wool ball. So this is actually something that does take place over the space of 5 minutes or so if you have a very long diffusion tube. If you have a shorter diffusion tube, you might find that this experiment works in a much faster way. But one thing that's really interesting for you to think about is how does the rate of diffusion within gases compare to the rate of diffusion in liquids? Now, somewhere else on my channel, I actually have a video that actually also shows the rate of diffusion within a liquid. That actually shows solid potassium manganate crystals being broken up by liquid water. I could also do a further investigation with diffusion, and I could compare cold water and warm water and try and figure out whether I could predict correctly what would actually happen in terms of the different times that it takes for my purple crystal to diffuse. And one other final really interesting thought for us to think about as well is, does diffusion actually happen between two different solids? If it does, it's going to be pretty slow. But there is definitely evidence when you have two different metals next to each other that diffusion can indeed take place between one metal and the other. So there you have it. Really hope that you've enjoyed the video. We've now got a very definitive cloud that's in our diffusion tube, and I'll leave you to just watch that and wonder in awe and amazement. Thanks very much for watching. Take care. Hit that bell, like and subscribe. Thank you. Have a great year this year.